And the last thing for today's lesson, we need to be able to relate the lengths and the angles of vectors to each other. Now, this is really quite straightforward. I think you'll enjoy this. You just need to use basic trigonometry and Pythagoras' theorem. Now, one thing to note is that when we saw angles of inclination in our Year 11 Advanced Trigonometry unit, we defined them as only being between 0 and 180 degrees, or 0 and pi if you're working in radians. And that's because a line doesn't have any direction. So if you consider my pen as a line and we're looking at all the different angles it could take, we have a 0 angle of inclination, and then the numbers get bigger, 10, 20, 30, 40, 50 degrees, right up to 90 degrees, and then it keeps on going around. Once it's back around here at 180 degrees, it's effectively in the same place as a line as it was when it was pointing that way. And that's why our angles of inclination were always numbers between 0 and 180, because once we went past 180, say 190 degrees, that's effectively the same as the line that's got an angle of inclination of 10 degrees. But vectors are a little bit different from lines. They're directed intervals, and so the direction makes a difference. So looking at my pen here, the direction it's pointing, where the blue lid is actually going to be different as it does a full 360 degrees. And so that's why our angles of inclination in this topic are going to be in all four quadrants. You might also have two names that you can use for them. For example, if you have an angle that looks like this, say, and it's down here, you could call it minus 30 degrees, or you could call it positive 330 degrees. And both of them would be acceptable answers. So just look for the context so that you can choose an appropriate solution. You do need to pay attention to direction though, because if we're solving something, tan of theta equals something, and we're like, oh, that happens in two different quadrants, there'll only be one of those answers that's the correct direction. Does that make sense? So here are the four rules that we can quickly and easily derive by comparing the lengths and the angles. If we have some vector u, and we define that it goes from the origin, O, to some point, P, x, y, then we can see that this is the x value that we have here, and this is the y value, which we have written here. Now, this is x, sure, but also remember that this length here is x, and this length here is y. So we've labelled this entire ray theta, but remembered also that that means that this angle here that the ray is making with the horizontal is theta. Sorry, that looks like a bit of a smudge. That looks a bit better. So if we just looked at Pythagoras' theorem, we could say this side squared is equal to this side squared plus this side squared. But notice the disclaimer here, we've got absolute value brackets. Now the reason for that is that if u is a vector, this one is a positive vector because it's going in only positive directions here, but it could be going anywhere at all. So we need to take the absolute value of that, because that's finding the length. It's taking direction out of it. It's just saying, what's the length of that thing, the absolute value? Let's square that. And then x and y are also lengths. We know that we need to square those. Now we can take the tan, sine, or cos of this angle theta. Now if we take the tan of theta, we're just going to get opposite over adjacent, y over x, and that will be the coordinates of your point. When we take sine or cos of theta, what we're going to find is that we get something over the vector itself. So then we can express x or y actually in terms of the vector. So x will be the vector multiplied by cos of theta, and y will be the vector multiplied by sine of theta. In this example, a vector has a magnitude of 6. Now that just means that its length is 6 units, and it has an angle of inclination of pi on 4. Now, angles of inclination start heading straight off that way to the right. So that means that pi on 4 means that it's coming up here at 45 degrees from the horizontal. So I can draw up an axis here. I know it's going up at 6. Okay, so sorry, its length is 6 units. So what I want to find is its component and its column form. I'm going to need to know the dimensions. I need to know this length here, and I need to know this length here. So what to do? Well, think about what you know here. You've got 45 degrees, and you know the sine, the cos, and the tan of 45 degrees as exact values, so they could be handy. And you've got this 6. Now you know that a 45 degree triangle with a right angle in it means that this side and this side are going to be the exact same. So find one of them and you'll have found the other one. So let's just start with something. We could do the sine or the cos of 45. Makes no difference really which one we find first. Let's do the sine of 45 and say that it equals, now we could call this y and we could call this x for now. We could say that this is y over 6, and that means that y is 6 times the sine of 45, which is 6 times 1 over root 2, which is 6 over root 2. We could also call that, multiplying the bottom and the top by root 2, we'll get 6 root 2 over 2, which is 3 root 2. That's a little bit tidier, I think. So if we've found then that this length is 3 root 2 and the other length is also 3 root 2, then if we want to get from here, the origin, to here, where our point is, then clearly we have a vector here of 3 root 2i and a vector here of 3 root 2j. So then we can say that our vector, let's call it, we'll just write vector, equals 3 root 2i plus 3 root 2j, and it's also equal to, in column notation, 3 root 2, 3 root 2. And that was quite simple. Our next example, find the vector of length 10 whose position vector has an angle of inclination of 150 degrees. So let's draw up an axis here. Now 150 degrees starting from this way is coming around like this, so that we've actually got 30 degrees in there and 150 degrees out here. Now if the length is 10, sorry, a bit dodgy there, let's just make it go like that, then what we need to find is how we get from here to describe this vector. Now it hasn't told us whether to use component or column vector, so we can take our pick. So what we need to find then is this length here, x, and this length here, y. And it's worth pointing out that there's a number of different ways that you can solve a problem like this. So instead of feeling stuck, just start with something that you know. You've got 30 degrees here, and you know what the sine, cos, and tan of 30 degrees is as an exact value. You've also got 10 here as your hypotenuse. So thinking of the simplest fact I know about 30 degrees is the sine of 30 degrees is half, isn't it? So if I say, all right, the sine of 30 degrees is actually going to be opposite, which is y, over 10, but I know that this side is actually a half, and that's equal to y over 10, then I can clearly see that y must be 5. Okay, so now I've got 5 in here, I can jot it down, and now I can use either, really I can use the tan of 30 degrees to compare these two, or the cos of 30 degrees to compare these two. Take your pick, I'm going to go for tan. So tan of 30 degrees is going to be 5 over x, and I know that the tan of 30 degrees is 1 over root 3, and that's equal to 5 over x. So that means x times 1 is equal to root 3 times 5. So that means down here I have 5 root 3. So then this vector is going to be, now think about direction here, we need to go left 5.5 root 3 units, so we could write it like this, and then we need to go up 5 units, so we could write it in component form, or we could write it in column form quite easily like that. Now you might notice that my working here didn't use the formulas that I just gave you. Why not? Well, I find it hard to necessarily memorize a whole heap of formulas. They're not on my reference sheet, but I do know how to use basic trig. That's something that I've known since year 9. So to me, it just made sense to lay out what I knew and to problem solve it. If you'd rather use those formulas, you can, but just be really careful. For example, the formula said y equals the absolute value of your vector, let's call that u, I suppose, multiplied by the sine of theta. So we could have jumped straight in if we used that formula and said, all right, the absolute value of our vector is 10, and we're multiplying that by the sine of 30, and that would have given us 10 multiplied by half, and then we would have got our 5 that way. Now, exactly the same working. The disadvantage of it perhaps is that this one might rely on you memorizing it, and you might make a mistake and think y is, what was it, sine theta or cos theta, and get things the wrong way around. So I would recommend always just draw a picture and put the angles in that you know, and then just problem solve it using basic Year 9 and 10 trig, basic Pythagoras, and then think about your vector at the end as steps left and right, up and down. Last example now, find the length and angle of inclination of this vector. Now, first thing to do is just to draw it. We're going one step to the left and then 2 steps down. So it's going to look something like this, and our vector goes in that direction downwards. So length is easy enough. We've got a right angled triangle here. Let's just use Pythagoras' theorem. So 2 squared plus 1 squared is going to be 5, and that makes this root 5. So we can find that easily. Length equals root 5. The angle will be a little bit trickier though. I think it would be helpful to draw up our whole Cartesian plane here and think the angle of inclination of this needs to start over here to the right, and we need to find this whole angle here. So we're going to need 180 degrees plus this. So let's find theta and then add 180 onto that. So finding theta then, we're spoilt for choice. We've got 3 different sides. So we can use sine, cos, or tan. Let's go for tan. We can say that the tan of theta is 2 over 1, so it's just 2. So then theta is going to be the inverse tan of 2, which we'll need our calculator to find because it's not an exact one. And we get 63 degrees to the nearest, we're going to say it's roughly equal to that, to the nearest degree. So therefore, the angle of inclination will be that same angle plus 180 degrees, so it'll be 243 degrees to the nearest degree.